is the review for your test on factors and multiples. Problem number 1 says, it seems we are always finding the GCF and LCM of two or more numbers, the greatest common factor and the least common multiple. Why don't we ever find the least common factor or the greatest common multiple? We find the greatest common... First, in order to really answer this, we need to think about what are factors and multiples. Factors are the pieces of the number that when multiplied together with other pieces of the number give you the number. The number is the product in this case. And so, for example, oops, bad choice there. A number like 12 has factors like 4 and 3. These are the pieces of 12 that when we multiply them together give us 12. And so if we have two numbers like 12 and 18, we sometimes need to find the greatest piece that's common to both numbers, like 6, because we might have a problem where we want to divide things into groups and we want the largest possible groups, or we may just be simplifying a fraction, and we can do that by factoring out the greatest common factor of both to efficiently simplify the fraction. So the greatest common factor is useful. The least common factor, the smallest piece of the number, is not useful for anything, because no matter what numbers you're using, the least common factor will always be 1. The least common factor is always 1, no matter what 2 or 3 or 4 numbers you're using, because 1 is a factor of all numbers. It's not useful for doing anything, to my knowledge, with the numbers, or to solving any problems. When you think about multiples are literally multiples of the numbers. So again, with 12 and 18, multiples of 12 are 12, 24, 36, 48, 18, 36, 54. And so the least common multiple of 12 and 18 is 36. But 18 and 12 have another common multiple if I keep going. 72 is another common multiple. So how many common multiples do they have? They have an infinite number of common multiples. So we could never even find the greatest common multiple. And in any case, it wouldn't be useful for problem solving, because usually we want to find the first time some event happens at the same time for two periodic events. That's the type of problem you would use. Or for creating equivalent fractions, the least common multiple will be the least common denominator. I mean, you like to keep your denominator as small as possible while creating a common denominator, so that the numbers don't get ridiculously large. You need to create like terms to add fractions or subtract fractions or compare them, but you'd rather deal with the least common denominator rather than some huge denominator. So the greatest common multiple of 2 or more numbers is always going to be some infinitely large number that we could never even find anyway. Problem 2. 561 is the product of 3 prime numbers. How many factors of 561 are not prime? And list them. This is an interesting problem, because the way it's worded and what it's asking you to do, because typically for problems like this, we're either going to be looking for prime factors or for all factors. And in this problem, it's useful to find both the prime factors of 561 and all of the factors of 561. And in fact, you could just do all the factors, because that will reveal the primes, but the primes are more easily revealed using the model we use to find prime factors, which is the factor tree. So let's do that first. Anytime you're looking specifically for prime factors, a factor tree is most useful. I like to start with the smallest possible prime factor, but I know 2 is not, 561 is not divisible by 2, because the 1's digit is not an even number, or multiple of 2. Then I consider 3. 5 plus 6 plus 1 is 12, so I know 561 is divisible by 3. It's when I think of this, I think of 540 is 180 times 3, and that's another 21 more than that, so 187. That's how I get that other factor. But you can You can get that other factor by just dividing 561 by 3. 180 tripled is 540, and then 7 tripled is 21. So yes, I feel good about my choice here. Now 187, again, we know 2 cannot be a prime factor, because if it could, we already would have found it. What about 3? 8 plus 1 is 9, plus 7 is 16. No, that doesn't work. Don't have to consider 4. 5 doesn't work. It doesn't end in a 0 or 5. I mean the ones place. If 2 and 3 don't work, 6 doesn't work. Maybe 7. 187 divided by 7. I'm going to think of that as 147ths, because I know that's 20. And that leaves me with 47 more sevenths. But I know 47 is not divisible by 7, so the whole thing's not divisible by 7. 8 I don't have to think about, or 9, or 10, about 11. Actually, I know 11 works just by looking at it, because the sum of these alternating digits is 8. This is 8. 8 minus 8 is 0, so this must be divisible by 11. 187 divided by 11. 1. Subtract to get a difference of 7. 77, so 11 multiplied by 17. And there they are, the 3 prime numbers, whose product will give you 561. In other words, 561's expanded prime factorization is 3 of 11 of 17. And you might think, why did we bother doing that if we're going to have to find all of the factors anyway? I think finding the prime factors using the factor tree is more efficient. And then when you go to do your UT diagram to find all of the factors, you'll see how useful it is to already know the prime factors ahead of time. I know I'm going to start with 1 multiplied by 561. I know 2 doesn't work. I know 3 works because I found it up here. 3 times 187. No 4, no 5, no 6, no 7, no 8. I already did all this, right? Well, I know I'm going to go all the way to 11 to find the next one. And it's 11 multiplied by 17. I don't have to think about 12, 13, 14, none of these. I mean, if any of those were possible, I would have a different prime factorization. So this is all of the factors of 561. No, it's not. I did it wrong. Hold on a second. I'm glad I looked at my key. 11 multiplied by 17 is not 561. Many of you may have caught my mistake when you looked at this. Okay, so that's what I get for going too fast. But if we associate our prime factorization here, 561 is also equal to 11 multiplied by 3 multiplied by 17. I just associated my expression here. So 11 multiplied by this product is 561, not 11 multiplied by 17. And 3 17s is 51, so 11 multiplied by 51. But you still see how knowing the prime factorization helps you find that other that factor pair more quickly, more easily. It would have been very easy if I would have done it right in the first place. And then I don't have to check 12, 13. 13 would be up here if 13 was a prime factor. 14, 15, 16, but we know 17 works. So 17 multiplied by, again, I'm just going to look up here. 17 multiplied by this product, 33. And then I'm done. Okay, then we just have to, I say we just have to do this, but actually this is sometimes the most important part of the problem, especially if you're taking a test. You do all this hard work, make sure you don't forget to answer the question that's being asked, because we haven't yet done that. 561 is the product of 3 prime numbers. Okay, we found those. How many factors of 561 are not prime? We have all the factors of 561 now. So let me just circle the ones that are not prime. 1 is not prime, because 1 is not prime. 1 is neither prime nor composite. But if it's asking for not prime, it's not saying composite, it's just saying which factors are not prime. So 1 would certainly be one of them. 3, of course, is prime. 11 is prime. 17 is prime. 33 is not prime because it's 3 11s. 51 is not prime because it's 3 17s. So 51 would be on our list. Did I do that right? Yes. 187 is not prime because we see it's semi-prime. It's 11 multiplied by 17. So 187 would be on the list. And of course, I should be circling these to be consistent. 561, of course, is not prime because we found many factors of 561 other than 1 in itself. So there's the list. Okay, problem number 3. Out of 50 families in a certain town, 20 own a dog and 35 own a cat. If 2 families don't own either of them, what fraction of families owns both a dog and a cat? Once you've done enough of these type of problems, you immediately, as you're reading it, recognize, it's going to be useful to use a Venn diagram model for this. So let me make a Venn diagram. Slowly, I've learned, works better on the writing tablet that I'm using. And the categories I'm comparing are people who own dogs, people who own cats, and then I'll read through it again. Out of 50 families in a certain town, so I can't use that, but I know the sum of all my addends in my Venn diagram, inside and outside of my Venn diagram, will add up to 50. 20 own a dog. I can't do anything with that because this piece plus this piece have to add up to 20. 35 own a cat. Again, I can't do anything with that yet. If 2 families don't own either of them, so the 2 families that don't own a cat or a dog are part of the 50 families, but they go outside, what fraction of families owns both a dog and a cat? This is one of those problems like we did in class where I have to consider, let's just consider the scenario where I have 20 owning only a dog and 35 owning only a cat, as if no families owned either. That would be a total of 55 plus 2 or 57 families. But we only have 50 families. So that difference tells you what the intersection should be. There should be 7 families owning a cat and a dog, both a dog and a cat. And that changes this number then to 13, so the sum is 20. It changes this number to 28, so the sum is 35. And then you check your work by adding these up. 13 and 7 is 20. 20 plus 28 is 48, plus 2 more is 50. So we feel good about our Venn diagram. And then again, the same thing we talked about on the last problem. Read back through the question and make sure you answer what the question is asking. What fraction of the families owns both a dog and a cat? Well, seven families own both a dog and a cat. That's the part. The whole is 50 families, so 7/50ths. Answer choice A.
Problem number 4 on the review says a dance-off is proposed as a new Spirit Week activity. 66 6th graders, 110 7th graders, and 132 8th graders will participate. Each dance team will include some 6th graders, some 7th graders, and some 8th graders. If all teams have the same number of members from each grade level, what is the largest number of dance teams that may be formed? How many 6th graders are on each team, how many 7th graders, and how many 8th graders? So this is one of the kind of problems where you can almost, if you do enough of these problems, you can almost tell it's either a GCF or an LCM problem. And so our Venn diagram model is going to help us answer all the questions and calculate all the numbers. But what is it, GCF or LCM? Well, we're taking these numbers of students and dividing them into teams. And if you're dividing the numbers, you need factors of the numbers. Because it says we want the same numbers from each grade level, that's going to be a common factor. And the largest number of dance teams that may be formed tells us that we're looking for the greatest common factor. And so let's start to set up the Venn diagram using these numbers. The 6th graders, there are 66 of them, which is 2 33s. 33 is 3 11s. 7th grade has 110 students. That's 2 55s. And 55 is 5 11s. As I find prime factors, I circle them. The 8th graders have 132 students, which is 2 66s, and 66 is 2 33s, and 33 is 3 11s. Now, you don't have to, I like to identify the smallest prime factor I can as I'm going through this so that I get my expanded prime factorization in ascending order. But it's not required. Of course, the fundamental theorem of arithmetic tells us that any any number that's greater than 1 is either a prime number itself or a unique combination of prime factors. So no matter how you broke these down, if you did it correctly, you and I should both end up with the same prime factorization. I'll make my Venn diagram now, 3 circles. When I make the second circle, I start inside the first circle, so my intersection is sufficiently large. And I do the same when I draw the third circle inside the other 2 to get sufficiently large intersections in case there might be many prime numbers going into those intersections. And then for a word problem, it's important to label not only the number, but what it represents. So these are our 6th graders. 66, 110 represent the number of 7th graders, and 132 is the number of 8th graders. The smallest common prime factor that all 3 share is 2, so I'll place a 2 in the intersection of all 3. And then they also share a common prime factor of 11, so I'll place that in the intersection of all 3. I see that I have a remaining 3 for 66, and there's also a 3 for 132, so I'll cross a 3 off of each of those trees and place it in the intersection of 66 and 132 only. This remaining 5 for 110 is not shared by any other number, so I'll place it in the 110 only section, and this final prime factor of 2 in the 132 only section. And then we learned to focus on the circles now. So this, if I focus just on this circle, I'll see that that kind of obscured. I kind of wish I hadn't done that. I'm going to fix that real quick. Okay, let me try that again. I think I just need a different color. Maybe, okay. If I focus just on the 66 circle, I see that I have 2 times 11, or 22 times 3 is 66. And so if you focus on one circle at a time, you learn how to do that just using your hand in class, or block out the other circles and just focus on one circle at a time. For the 66, I have 22 times 3, that is 66. If I focus just on the 110, 22 times 5 is 110. And then on the bottom circle, we know that these are 66, and 66 doubled is 132. And so I feel like I've set up my Venn diagram correctly. Then to answer the questions, we talked earlier about why this is a GCF problem. And the greatest common factor of these 3 numbers would be the product of the prime factors in the intersection, or 2 times 11, which is 22. But then you have to make meaning of that 22. We are dividing these students into teams, and the greatest common factor would tell us the largest possible teams that we could make, the largest possible number of teams. So we can make 22 teams of dancers. That's the answer to the first question. The second question, how many 6th, 7th, and 8th graders will be on each team? Well, if you focus just again on this 6th grade circle that I've highlighted in yellow here, the GCF, the 22, tells you how many teams you have. And if you have 22 teams but 66 6th graders, you just look inside that circle and you see that 3 22s equals 66. So there must be 3 6th graders on each one of those teams to make up the 22 teams. 3 22s is 66. So there are 3 6th graders on each of those 22 teams. Each of those 22 teams has 5 7th graders. And the 22 teams, now focus on the whole bottom circle. Now we're talking about the 8th graders. How many 22s equal 132? Well, outside of that 22 is a 3 and a 2, so 6. 6 22s, so 6 8th graders. And if you wanted some way to check your work, 6 plus 3 plus 5 is 14. And you just make sure 14 times 22 is equal to the total number of students. 14 times 20 is 280. 14 times 2 is 28. So we have 308 students, and the total number of, if you add the 110, the 132, and the 66, This is 198, 208, 308. So that checks out. Just a way to check your work. Okay, we'll pick up the review with the problems on page 2 on the next video.